Hi everyone, in this video we are going to create a sequence recognizer in Intel Quartus Prime. This video assumes that you have watched the LabBot explanation video, which covers this in more depth. In that video, you were introduced to this two-input example on the screen. We then assigned state codes to it, with A being 0 and B being 1, and then we generated the state table, where an input of 1 on X would move us to the next state, and then a further input of 0 would unlock the system by producing an output of 1. So when it comes to converting this into a Boolean expression, which allows you to create your circuit in Intel Quartus Prime, basically you're treating this like a K-map. So then you look at the areas which are 1 for the next state, and then for the output one, you'd treat that the same way. So let's do the next state. So I'm going to treat present state as D0, and then I'm going to treat X as, X. So with this one, we have not D0 and X. For this one, we have D0, not X. So pretty much what you want to do is you want to put these together, just like this. So this will generate ones for the specific areas that you want to change this next state to. That way, when your combinational logic circuit behind the D input of the D flip-flop, then it will pretty much read that on the clock signal and then generate that next state, creating a sequence recognizer sequential logic circuit. Okay, so let's do this in Intel Quartus Prime. Okay, so over here we have a new schematic for Intel Quartus Prime, and now we're going to create our sequence recognizer. So to do this, what we need to do is we need to grab one D flip-flop. This is because we are storing one bit of information in D0. So this flip-flop will represent our D0. And the input to it will represent the D0 at the next state. So behind this input, we need to place our combinational logic circuit. So our combinational logic circuit is D0 not X or not D0 X. So let's place that down. So D0 is the current state of this flip-flop. So what we're going to do is get two AND gates. Two input AND gates, sorry. And then one OR gate. And that would be a 2-input OR gate since we have two AND gates. And as per usual, I'm lining these up to make it a bit neater. Okay, now I'm going to connect them up. Okay, and now I'm going to create an input marker to represent our input, X. And then I'm going to also create an output marker to represent the output of the current state. I'm also going to put the output of the actual output that we've designated in the state table. So the reason why I've done this output for the present state is because sometimes it's useful to know the present state outside of your specific block. This will allow you to track the state of the circuit. So I'm going to call this D0 and then this one out. Alright, and I also need a clock input. But with a sequence recognizer, you need to be very careful about where this clock input comes. Because with the clock input, the state will always change when it goes from low to high. Which means that if you connect this to your main clock, in in a complex circuit, that main clock could be running at 50 megahertz. So you can imagine that it's changing state 50 million times a second. And for a sequence recognizer, if you're doing manual input, then this wouldn't be ideal because you would not be able to be fast enough to press those inputs in. Okay, so now I'm going to connect the inputs together. So let's have a look. We've got D0 not X and not D0 X. So I am missing a logic gate and inverter. Okay, so as we see, it's D0 not X. So let's connect it up. So we feedback from D0. And then not X. And then we're doing not D0 and an X. So with that, you need to use a separate inverter for D0. Again, this is not the neatest way you can do it. So I'd highly recommend that you try to make it as neat as possible by pre-planning ahead. Okay, so that's done. Okay, now I'm just going to connect the clock up. Okay, so that's done for the sequential logic side of the circuit. So we have D0 and not X, and then not D0 X. Now what we want to do is connect the output circuit, but this needs to be fed through another combinational logic circuit. So to do that, all you need to do is just look at where the 1 is here, which we can easily see as D0 not X. So let's put that into this output marker now. And connecting at the output, and then we're done. So this is your circuit, but you will also need to make sure that your reset system can also handle the sequence recognizer. So now what I'm going to do is I'm going to create the reset circuit. So as you've seen in previous videos, the D flip-flop in Intel Quadus Prime is active low logic for resets, so we are required to put this NOT inverter just before the reset line. Okay, so let's connect that up now, and then I'll create an input marker for reset. Okay, so with this circuit, it is very messy. You definitely could make it a lot neater, but for the purposes of this example, this is sufficient. Okay, so this is our circuit.